Since we are done with the measure part, so now we are ready to use the measure theory to talk about integration. So what our goal is? Our goal is today Lebesgue integration. So Lebesgue integration. Okay. So first we want to talk about what if f is simple. What if f is a simple function? Okay, so what is a simple function? So simple function is nothing. Okay, so simple function. So a function, f is simple, if it has only finite number of values. If it takes on only finite many values. We have another definition, kind of mathematical. So mathematically, how can we define? So we say that suppose x as mu is a measure space. Okay, and then f from x to r is simple, means we can write down f is equal to sum of k is equal to 1 up to n ck and characteristic function of ek, where ck are the distinct non-zero values of f. Okay, and what are those ek? So and ek is nothing but obviously this is ck, and this will be nothing but x belong to e such that f of x is equal to ck. Okay, now if we have simple function, then what about the integration? So whenever we have a simple function, so the integral of simple function, so we assume that f is simple function, and that simple function we can write down sum of k is equal to up to n ck characteristic function ek d mu. So we will always define it this in a way that this is the integration is nothing but sum of k is equal to 1 up to n ck and measure of ek. So that is the first definition, that what is the integral of the characteristic of the simple function. We also have what if we have characteristic function. So the integral of the characteristic function is nothing but this is measure of e. So in example, if we see that if we have set q, then this is measure of q and measure of q is 0. And also if we take another set, suppose 0 1 difference q d mu, what is the integral of this function, characteristic function over the set? So this is measure of 0 1 difference q, but we all know that this measure is 1. And how you can prove it? So that is we have now based on, since we have a definition of simple function, so we can just go ahead and do proposition. Proofs are very easy. I'm gonna skip all those proofs because very easy. So if f from x to r is measurable, simple, and if we have any number a belong to r, then af is simple, measurable, and the integration of af d mu is nothing but this is f d mu. So the proof is like very easy. You can easily show that, okay, so we know that if we have any measurable function and the constant multiple to that measurable function is again a measurable function, and also you can show that the constant multiple to measure a simple function is again simple, and a f d mu is a integral f d mu. This is like very easy. So how? So proof is, I'm gonna prove just this part so that you can have a little bit idea. A f d mu. Okay, so how can write, we rewrite f, so this is sum of k is equal to 1 up to n ck characteristic function ek d mu, and now we can rewrite this is sum of k is equal to 1 up to n a ck characteristic function ek d mu. And this, what is this? So now since this is, so we know that this is nothing but this integral is equal to a, and what is this thing? So this integral is what? The measure of, so ACK, measure of characteristic EK by definition, right? Now again, how can we rewrite? So we can rewrite this is a sum of k is equal to 1 up to n ck measure of characteristic function ek. But again, what is this sum? This sum is nothing but this is f d mu. So done. Okay, so that was very easy result. You can easily prove this thing. But the most important proposition in this section, so today this section is all about if we have measurable function, then what is the integral. So we saw that what is the integral, and then based on this definition we have proposition. So we have second proposition, which is kind of order preserving, that if fg are simple and measurable and they are non-negative fg, so f is greater than, we have function f is greater than, so g, okay, so f is greater than, g is greater than 0, then what we can have, then integral of g d mu is less than integral of f d mu. So proof is very easy. So you can show that, okay, that fg are measurable and fg is greater than 0. So now our goal is actually to do this thing. So first of all, what do you think about the addition of two measurable function is measurable? Okay, so this is, and also this is simple and measurable, well known fact. Okay, sum of two measurable function and sum of two simple function is simple. And also, what do you think about this f minus if we have a non-negative as well? So if we have non-negative, f minus g d mu integral is always greater than or equal to 0. Now we need to show that this inequality holds. So what do you think about the integral of f d mu? How can I rewrite? I can rewrite this is f minus g plus g into d mu. Okay, now actually, so whenever we have simple functions, so note is that if we have two simple function f1 plus f2 d mu, okay, this is always equal to f1 d mu plus f2 d mu. You can easily prove that, but I skipped actually. So now since f minus g is simple, g is simple, so we can just go ahead and use this property. So this is f minus g d mu and plus g d mu, but this is greater than or equal to 0. So this means that this inequality is greater than g d mu, hence we are done. So this was very easy. Okay, now we have another proposition. Okay, so another proposition is if we have if e1 e2 up to so on en belong to S, and a1 a2 up to so on an is greater than or equal to 0, then sum of k is equal to 1 up to n ak characteristic function ek is actually sum of k is equal to 1 up to n ak measure of ek. That's we already saw in case of that was actually the definition of the characteristic, the definition of the integral of the characteristic function, but we're gonna prove that. So proof. Now since we already know that, so by induction we know that sum of k is equal to 1 up to n ak characteristic function ek. So this is sum of k is equal to 1 up to n characteristic function ak and ek d mu. That's by induction. Okay, but now since we know that if we have if you have, so if we have cf d mu, I can write down that this is cf d mu. Okay, so by this fact, so this is sum of k is equal to 1 up to n, and this is ak characteristic function ek d mu. Now this is sum of k is equal to 1 up to n ak. What is the integral of characteristic function? So this is measure of ek, and hence we proved. Done. Okay, so but now we will actually talk about something more. So now actually we discussed when f is, what is the integral of characteristic function and what is the integral of simple function, and based on those we have proposition that's well established, but I again proved them for you. So if you have any question, you can ask. Now in the next video we are gonna talk about if we have any non-negative measurable function. So we forget about the case that okay, if we have simple function or if we have characteristic function, but now we will generally talk about if we have non-negative measurable function, then what will be the integral of that kind of functions. Okay.